We're on 2.2, and we just finished example 4. So we have this idea of the limit. Remember, the limit is the notion of motion, right? It's the idea of moving towards a point and getting infinitely close to it. And as we do that, we check to see what the y values are getting closer and closer to or approaching. Whereas the function value is a stationary idea, right? It's like what is happening at that point. Is there a dot? Is there not a dot? The limits are the roads coming in from either side, and the function value is analogous to a bridge over a canyon, right? So now that we have this idea of the limit, we can define graphical features that previously were really undefinable, like a vertical asymptote. So what do we know about a vertical asymptote? What do you know about it? What do we abbreviate it as? We call them VAs. And what else do we know about them? They're semi-permeable membranes, right? Is that right? So as you're approaching one, you can just kind of sneak through one of the holes like that? Like diffusion? Is that how it works? No. What else do we know about vertical asymptotes? Are they really on the graph? Do graphs really have dotted lines up and down? No. We just draw those in there to show where this imaginary kind of force is. It's like a black hole force. How do we find vertical asymptotes from the equations? Do you all remember? Sure you do. It's a discontinuity, yes? We know that. A vertical asymptote is a discontinuity. It's of the form x equals a number, call it c, the discontinuity. But how can you identify that it's a vertical asymptote just from the equation? A discontinuity causes a what in the denominator? A 0. But a vertical asymptote also causes a what in the numerator? Nope. A number other than 0. Yeah, good. 0 over 0 means whole unless it's jump man, and it's a jump. But any non-zero over 0, when you plug in, means that the graph has a vertical asymptote there at x equals the number you plugged in. So it could be 5 over 0, 4 over 0, negative 100 over 0. Non-zero over 0 means vertical asymptote. Now, think about what your options are. If it's not a semi-permeable membrane, what are your options as you approach, let's say, that purple vertical asymptote from the left? Here I am. I'm approaching the vertical asymptote. What are my options? I can go up or down. As I get closer and closer to it, it is like this crazy force, and it's going to force your y values to either go up to what? Infinity? Or, yeah, depending on what the equation is, it could head right down to negative infinity. Now, can it do both of those on one side of C? No, because then it, bless you, would not be a what? A function. It would fail the vertical line test. But it could do one or the other or neither. Okay, some functions only live on one side of their vertical asymptote. But if it's doing anything, it's going to do one of those two things. And similarly, on the other side, you have those two options. So, how can we then define a vertical asymptote using the limit? Does the function value exist at C in this example? Is there a dot anywhere on there? No, but aren't we still interested in the behavior in the neighborhood or the vicinity of x equals C? Yeah. So all we have to do is talk about what happens as we drive on the roads as we get closer and closer to C from both sides. So let's go ahead and just say it, and then we'll look at it. The limit as x approaches C from the left could either equal what? Infinity, or the limit as x approaches C from the left could equal negative infinity. And then the exact same thing from the right. The limit as x approaches C from the right could equal infinity, or the limit as x approaches C from the left could equal negative infinity. If any one of those four things happens, any one of those four things, we're going to have a vertical asymptote at x equals C. Or if we have a vertical asymptote at x equals C, then any one of those four things could be happening. It works both ways. Okay? Now, let's define that. Here it is in the box. And it's exactly what we said. If, it's an if and only if statement, so if the limit as x goes to C from the left, where C is just some x value, of the function equals infinity or negative infinity. That means if we approach from the left, it either goes up or down forever and ever and ever, and or. So one can happen or both. The same thing happens from the right-hand side of C. It goes up or down, unbounded to positive or negative infinity. Then we know that there is a vertical asymptote at x equals C. Okay, and it is a vertical line, x equals C. And it works in reverse again. So it's an if and only if. If we know there's a vertical asymptote at x equals C, then of course one of those four things has to be happening, for sure. It is a discontinuity. Now, let's kind of just think about what we're saying, first of all, when we say the limit equals infinity. You're actually saying two things. When you say the limit equals infinity, first of all, does the limit exist? If I say the limit is 4, then the limit exists, right? It's 4. But if I say you have infinite potential, and you do, am I putting any limit on your potential? No. No. So infinity is not a limit, okay? If I say you have negative infinite potential, would that be nice? That would not be nice, because then there would be no limit as to how bad you can be. All right? But again, infinity is saying two things. It's saying, first of all, the limit doesn't exist. But it's also telling you why it doesn't exist. And why is it not existing? Because your y values are increasing without bound, we say. They go up forever. So it's a very, very meaningful answer. It tells you it doesn't exist, and it tells you why. Same thing if you said the limit was negative infinity. You're saying the limit doesn't exist because it decreases without bound. Now, we saw yesterday a limit that also did not exist, but it was not because the y values increased or decreased without bounds. What did we see yesterday where the limit did not exist? The what? Don't make me dance all day. What's it called? What's out of discon? A jump, right? Because remember, for a jump, the limit from the left has to be finite, and the limit from the right has to be finite. But if they are different, what did we say about the general limit? It does not exist. So limits can fail to exist for a multitude of reasons. It's kind of a catch-all category, which the calculus kids have kind of prescribed to this idea, which I don't know if I should tell you. When evaluating a limit, when in doubt, D&E, right? When in doubt, D&E, because you know what? It covers a lot of things. But I tell them, right after they say that, hey, don't be in doubt. And they're like, okay. So then they don't have to use that little thing. But things can fail to exist for multiple reasons. So infinity is a very descriptive answer. You ready to try it out? Let's try it out. Example 5. Sketch the graph of f of x equals negative 4 over x plus 2 using your knowledge of parent functions and transformations. Oh boy, we get to do that. Step 1, identify the parent function for negative 4 over x plus 2. We've already talked about them this year a little bit. Strip away all the negatives and numbers, and what are you left with? X in the bottom, so 1 over x. Yeah, the parent function is 1 over x. So let's kind of just review what that guy looks like. That function's name is f, so I'm going to call this guy g. G for Gordon. All right, so 1 over x, 1 over x, 1 over x. That's the parent function, or the mother function. I guess if it's a mother function, not only do we have to be careful how we say that, but we should give him a different name. How about Glenda? Glenda. The good witch of the Precal class. 1 over x has a vertical asymptote on the y-axis and a horizontal asymptote on the x-axis, and the reciprocal of a positive number is a positive number, and the reciprocal of a negative number is a negative number. So there's your function 1 over x. It's a hyperbola. Hi, hyperbola. How you doing? But it's rotated 45 degrees. It lives in quadrants 1 and 3 with 2 asymptotes that are the x and y axes. Okay, so if I want to quickly sketch f of x equals that, I need to put it into standard transformation form. And it's almost there, almost there. All I really got to do is bring that negative 4 out front, not just the 4, and then it would be time 1 over x plus 2. So there's standard transformation form, because that's really like negative 4 over 1. Okay, so let's go through the transformations. And you do this from left to right, which is why it works so beautifully. Always multiply before you add and subtract. So what does the negative in front of any function do to the function? Flips it or reflects it across the what axis? X-axis, okay? Good. So that's going to make this graph, I'll just kind of use like a light yellow here. That's going to make it live down here now in quadrants 4 and quadrants 2, right? So that would be negative 1 over x. All right, what does the 4 do to it then next? If it's out in front, you multiply your f of x values by 4. Remember, f of x is also another name for y. That is a vertical stretch by a factor of 4. Now, that's one that you don't have to show, because that's not going to really change anything except the graph is going to be a little bit steeper, okay? So I'm not going to redraw that. We don't really show those. But the important one is x plus 2, because that picks the graph up and shifts it what? Left to. It's the inside with the x, so it shifts it left to. So the vertical asymptote, which was at 0, is now where? -2. You could have figured that out just by looking at it, right? -2 is not in the domain. When you plug it in, it causes -4 over 0. All right, so let's go ahead and sketch the graph then. And I'll use beefy brown. And I'll use a little bit bigger line quality here, okay? So let's just sketch it over here. Here's -2. Those are your vertical asymptotes. And then here's your horizontal asymptote. So notice now it kind of looks like we've created a new x and y axis, right, with our new asymptotes. And all we have to do is say that it lives down here. Oh, that's pretty. And over here, oh, lovely. Let's go ahead and put a pretty little tree over here. You know, a little happy little tree. Right? Y'all watch Bob Ross on Netflix? God, it's addicting. Okay. Anyway, there it is. And now that you know what the graph looks like, you can answer the questions super, super fast and super, super confidently, right? Let's try them out. Question number A, which is really a letter. The limit as x goes to -2 from the left. -2 from the left. -2 from the left. Okay, so go over to the beefy bound graph. What are we approaching as we approach -2 from the left-hand side? We're going up to infinity. So you could say infinity, which is a very descriptive answer, right? Because you're saying two things. What two things are you saying? The limit doesn't exist, but you're also saying because, what are the y values doing? Yeah, they're going up forever. They're increasing without bound. They're going up, whatever. But guess what else also works? It's technically correct. And this is what she did in the movie clip yesterday. The limit does not exist. The limit does not exist. If you put D and E on a free response, guess what I'm going to do? I'm going to count it correct. Yes, I will, because it is correct. But if this were a multiple choice question, D and E would not be an answer choice. You'd have to commit to positive infinity, because it's a more descriptive answer. But on a free response, I wouldn't count it wrong. Okay? So keep that in mind. What if on a free response you put negative infinity? Now it's wrong. Now it's wrong. So really on a free response, it's almost safer to put D and E if you're not sure what type of infinity it is, right? Which is why the calculus kids say when in doubt, D and E. To which I reply, don't be in doubt. Okay. All right. How about this one? The limit as x goes to -2 from the right. -2 from the right. So here's the graph. Here's the graph. -2, let's approach it from the right-hand side. Whoa! Where are we going? Negative infinity. So that is the preferred answer, negative infinity. But of course, on a free response, you could cop out and say, I'm sorry, you could be safe and say D and E. D and E. Negative infinity would be the multiple choice answer, though. Now, what could be said, if anything, on part C about the limit in general without the plus or minus? Remember it has to be D and E. Remember up here we said that the general limit is going to equal L if and only if it's L from both sides. Now, L is a finite number, but if it doesn't exist, you can only say infinity or negative infinity if it's going up on both sides or down on both sides, respectively. So in this case, we have to say D and E. You do not put plus or minus infinity. You don't put both. Okay? You just say D and E. Now, what is f of -2? F of -2. What do you, well, let's see. Well, you plug it in. Let's try it out. F of -2. I plug it in, I get -4 over 0. So what is that? Yeah, so what do we know about the function value? Does it exist? No. Anytime you divide by 0, the function value doesn't exist. The limit still might, but the function value, it's game over for the function value. So that's D and E. All right, so now part C, and I need to add something. I forgot to type in a negative. Is f of x continuous at -2? Why or why not? Well, let's think about that. Remember, we talked about continuity yesterday kind of intuitively, and we said it's continuous if we can drive our family safely across the canyon, right? Because that's what we want to do, which translates into there needs to be a road coming in connected to a bridge, connected to a road going out. If any one of those three things exists but are not equal to each other, like if I'm driving on the road and then I get to the bridge and at the end of the bridge, guess what? The road's over there. That's no good, okay? Or if I'm driving up like this and I get to the canyon and I see the road straight across from me but the bridge is over there, that's no good, right? So anytime the road, the bridge, or the road don't equal each other, any two of them, or any one of them fails to exist, it's game over. You can't cross. Now, it's real obvious that the function is or is not continuous at -2, just looking at it. It's not. But you don't want to say it's not continuous there because there's a vertical asymptote there. The vertical asymptote is actually a consequence of why it's not continuous, okay? And so we're going to look at that here after this example. So is f continuous at -2? No. Since what? What's the easiest way? If we need both a road and a bridge and a road all connected to cross, do we have any of those things? No. As we have the road coming in towards the canyon, the vertical asymptote, it kind of freaks out and goes up and runs now parallel along the canyon. Stupid road. And as we approach from the right-hand side, we want the road to go right to but it chickens out and goes down, runs parallel along the canyon. And of course, do we even have a bridge anywhere on there? No. So none of the three things exist that we need. We can't cross. It's hopeless. So all you have to do is cite one of them. No sense. How about f of -2 equals dne? That's the same thing as saying there's no bridge. And you turn around and go the other way, and the adventure continues, right? With the family in the back. Okay, so just as we can define discontinuities now, vertical asymptote in terms of the limit, we can rigidly define now in terms of the limit, guess what? Continuity at a point. We've been doing it kind of intuitively here, road, bridge, road, but here it is now. And if you can draw asterisks or stars, okay, or whatever symbol defines importance to you, draw a few of them over there, because this is a super duper important definition, and you'll be using it all through calculus as well. Continuous functions are very, very important in everyday life, okay? And so now we have a way, mathematically, to come up with a rigid way to determine if a function is continuous at a point or not. So here it is. The definition of continuity at a point, it's a three-step definition, so it's a three-step checklist. A function f is said to be continuous at x equals c. So when we say at a point, first of all, we're defining it at an x value, at an x location. That's our independent variable. So go to any x value, and now look at the graph there. Is it continuous? Well, yes. It will be continuous if and only if the limit from the left of that x value equals f of c, the function value there, which equals the limit from the right. That makes perfect sense to us now, right? Because that just means that the road equals the bridge, which equals the road, the y values of them. They all exist, and they are all connected at the same point. Now, if any one of those two things fails to exist, or I'm sorry, if any one of them fails to exist, or any two of them do not equal each other, then it's game over and the function's not continuous. Got it? If any one of them fails to exist, or any two of them do not equal each other, it's game over and the function's not continuous. But if all three of them exist and they all equal each other, then we could drive across safely. All right, so here's what we're going to do. We're going to start with two graphs, and we're going to kind of go through the notations, because it's very important that you practice proper notation from the beginning. So here it is on example 6. Use the three-step definition of continuity, that's the one right above, to determine whether this function below, whose graph is given, is continuous or not at x equals 0. Show your analysis with correct notation and give a concluding statement with the justification. Oh boy. All right, you're going to have to do this on the quiz tomorrow, so take special note. I'll walk you right through it. Here's what you could do each and every time to start it off. There's three things you're looking for, right? We're talking about at x equals 0. The function's name is f of x. So if you want to just start by doing this off to the side, we need the limit as x goes to 0 from the left of f of x. That's the road coming in. We need f of 0. That would be the bridge. And then we need the limit as x goes to 0 from the right of f of x. That would be the road going out. So off to the side, I'm not going to label it every time, but if it helps you with the analogy, that's the road coming in. There's the bridge. And then here's the road. Road, bridge, road. That right there is going to set you up for success, because the notation there is scrumptiously beautiful. It's a language. Look at that. And it's fully intact. So then all you have to do is come back and just evaluate it. So here we go. What's the limit as we approach 0 from the left on this graph? Well, watch my finger. Here's x equals 0, also known as the y-axis. As we get closer and closer and closer and closer to x equals 0, the y values are getting closer and closer to what? 1. Cool. Now, since I'm right here, let's do it from the other side. As I approach 0 from the right-hand side, my y values are getting closer and closer and closer and closer to what y value? 1. Also 1. Okay, so those are the two limits. I'm moving in towards 0. Now I want to know what f of 0 is. So now I go to x equals 0, and I look high and I look low for the dot, if it exists. Is there a piece of the graph at 0? Yes, and it's highlighted for you with a Rudolph nose. That is the y value. It's right there. See, I cover up the roads coming in. What is that dot's location? 0, 1. So, here we go. Let's come back over here. I think I remember what all three of these were. The road coming in from the left was 1. It was the same as the road coming in from the right. And then the function value was also 1. So if this were a quiz tomorrow, you would get a check, check, check. Oh, yeah. How easy is that? Easy. If you're missing anything, though, like the plus or minus on your limits, or you're missing an f of x, or you don't put f of 0, you put f of x, you're not going to get the check. Okay? Now all we have to do is use a three-step definition to determine if it is continuous or not, and then explain why based upon the definition. It's only continuous if all three of them equal each other. Do all three of them equal each other? Yes. So is it continuous at x equals 0? Yes. Now you want to get in the habit of writing a complete sentence. The function's name is f. So don't say it is continuous. Don't just say continuous, complete sentence. F is continuous. You don't even have to put of x because the function's name is f. F is continuous. Where? In France? At x equals 0. That right there is going to get another check. That's answering the question in the affirmative. F is continuous at x equals 0. Not it is continuous or it is continuous there. Don't use pronouns in this class. Eschew pronouns. Okay? Use the actual noun, proper noun. Since or because. Because is actually more correct, but it's a little bit longer. So no one's going to fault you for saying since. Okay? Since, and then what's the reason? Based upon the three-step definition. 1 equals 1. Because what do we need for it to be continuous? We need the limit from the left equal the function value equal the limit from the right. They all equal 1, so since 1 equals 1, that's your justification and that's your check. Now notice how nice that is. You do not have to rewrite the limit as x goes to 0 from the left or f of 0 or the limit as x goes to 0 from the right. That's a lot of writing. We did it one time and we labeled it 1, 1, 1. So down here, when you see that 1 equals 1, you're not like 1 equals 1. That's true. That's true. So it could also be continuous because since 5 equals 5. That's also true. Is that the reason it's continuous? Notice, if this were not up here, that would be kind of a silly statement, right? Since 1 equals 1. Very good, very good. Well done. But when you say 1 equals 1, you're looking at, what are you talking about? Oh, this one and this one and this one, they're all equal to each other. Good. All right? So super important that you label it up here. Now, could you just say since 1 equals 1? Or do you need all three? Seems kind of silly to put all three, right? Is it a two-step definition of continuity? It's a three-step. If you just say 1 equals 1, now I'm going to be like, oh, crap. Because I'll say that word. Which of these two are the important ones? Is it because the limit from the left equals the one from the right? Or is it because the function value equals the limit from the right? Which of those two ones are you talking about? Are you talking about all three? So there you go. How many checks is that worth? Count them. 5 checks on a quiz. Now notice we took something that was glaringly obvious. If you just looked at the graph, you'd be like, oh, yeah, continuous at x equals 0, right? Just looking at the graph, right through there. No problem. But we broke it down rigidly into mathematical statements. It's like a proof, irrefutable. Okay? Questions on that? Think you can reproduce that and you understand the idea? All right, let's move on to example 7. All right, so now we have this broken up graph, and I think it's real obvious just to look right here and say, I got a what at -4? A hole, I got a what at 1? A jump, and I have a what at 6? That's another hole, right. So those are easy to spot, but how can we justify them mathematically? We don't say that it's not continuous because there's a hole. We don't say it's not continuous because there's a jump. The jump and the hole are a consequence of how it's not continuous based on the three-step definition. So let's go ahead and set it up. We're looking at -4. The function's name is f. So road, bridge, road. We got the limit as x goes to -4 from the left of f. We got f of -4. And then we got the limit as x goes to -4 from the right of f of x. Now, if you notice the way I write my limit, I get a little bit hasty, right? It's just an L with a dot on it. As long as I can tell that you're writing the limit, it could be kind of, like a PhD limit, like how doctors write. But you need it there. Legible? It doesn't have to be cursive. No, I like writing in cursive. LIM, you see you're using script, yeah. It doesn't have to be cursive. Ooh, I like that one. Yeah. Jason just did like a real tall, skinny guy standing by some mountains. That's what he did. Real tall, skinny guy standing by some mountains. You know what? I would say, Jason, that looks really, really good, but the tall, skinny guy should be at the mountains with his son who's wearing a little ball cap. Okay? Okay? Or, you have it. Or if not a son wearing a ball cap, maybe a snowflake falling. Yeah. The dot on the I is kind of important. All right. So anyway, as long as I can tell there's a limit, you're not going to lose points. All right. So now let's go ahead and answer it. I've set myself up for success. As we approach -4 from the left, what y value are we getting closer and closer to? 2. What is the limit as we approach from the right? Also 2. So I'm going to come down here. That was the limit from the left is 2, and the limit from the right is 2. Now, that means that the general limit exists, right? That's all that means. The general limit then exists because the two limits are equal in 2. But that doesn't mean it's continuous, right? Because if we're talking about continuity, we can't just be looking at the limit because the limit are the roads. And if you drive across from one road, try to get to the other road without considering the fact that there is a what in between connecting them? A bridge? You might fall into a hole if there's no bridge. Yeah. Anyone jumped into a swimming pool? Yeah, I have, like once. But you know what I did before I did? And I hope y'all all did too, which I know you probably did because you're here. Just check to see if there's water in there, right? Yeah. I mean, swimming pools are supposed to hold water, but you'd be surprised. Uh-oh, my iPad's upside down. There we go. What's f of -4? F of -4. Look high, look low. Look high, look low. Do you see a dot? I don't either. So does it exist? No. All right. So is it continuous there? For sure it's not. But based upon the three-step definition, what is the reason? What reason are we going to cite? What reason are we going to cite? Very good. If any two of them do not equal each other, or any one of them, Blake, do not exist, then it's game over. Now, you don't want to say since 2 does not equal D&E. That's true, but that's kind of, right? 2 does not equal D&E. Unicorns does not equal leprechauns, right? Leprechauns don't exist, unicorns do. That's kind of a silly argument. It's best just to say leprechauns don't exist. So F is not continuous. Where in France? At x equals -4, since what? F of -4 equals D&E. Now let me show you how I'm going to score this one. I'm going to for sure give you a check for the justification. That's the last sentence. I'm going to for sure give you a check for the conclusion. And by the way, those could be flipped because the since part is an adverbial clause, and it can be moved around to the beginning of the sentence if you like. So you could start with since f of -4 equals D&E, comma, f is not continuous at x equals -4. However you prefer. But I'm not going to give you a check for all three of these because you technically, if we're checking for continuity, don't even really need to find the limits, do you? So I'm going to give you a check for calculating that right there. These would not need to be calculated then. You could certainly do it to be thorough, but I would not give you checks for them. And by thorough, I mean like complete and cover all your bases, not like Henry David Thoreau, okay? Because he just like farmed beans. Yes, Yes, that's exactly what I'm saying. That if you just wrote this sentence right there, you would get all three checks. Okay? You'd get one for the answer, you get one for the justification, and then one for knowing that you just had to consider f of 4 equals d n e. Okay? When do you have to find all three of those for sure? Only if it's continuous. So you keep finding them, And as soon as one of them doesn't exist, it's game over. As soon as two of them don't equal each other, it's game over. But if all three of them exist and they're all equal to each other, you keep going. All right, we've got to step up the speed here a little bit. Let's look at x equals 1. The limit as x goes to 1 from the left of f. The limit as x, I'll do the function value. I'll keep it consistent. Then f of 1. And then the limit as x goes to 1 from the right. So we wrote down the notation. And then 1 from the left. Here's 1 right here. What's 1 from the left? 4. What's the limit from the right of 1? -2. Oh, boy. So 4 from the left, -2 from the right. Technically, do we need to even find f of 1? No, we don't have to. But notice that f of 1 is also the same as the left-sided limit. So you could say 4. I don't care if you find all three. Again, that's being thorough. But here's how I would award the checks. I would give you one check for finding either one of those, or both, just one check. And then, of course, one check for finding that. And now you would just say f is not continuous at x equals 1. That's a check. Since, and then again, refer to it. 4 doesn't equal -2. Check. That's your justification. Now, just a word of caution. If you ever give more information than you have to, and it's wrong, you're going to lose a point. So let's say that you only needed to calculate one of these two that had a 4 in it. But you calculated both, and for some reason you called one a 4 and you called one a 3, and this was a -2. Well, now, one of them is not a 3. You miscalculated. You're going to lose a point. So just be aware of that. And then finally here at x equals 6, let's get the machinery up and running. The limit as x goes to 6 from the left of f. F of 6, and the limit as x goes to 6 from the right of f. Equals. Okay, and now that we have it all set up, it's just kind of a look and drop them in there. Does the general limit exist at 6? Does the general limit exist at 6? Yes, it does, because the limit from the left of 6 is 5, and the limit from the right of 6 is 5. And so you could just throw that in there, 5 on the top, 5 on the bottom. And what is f of 6? Yeah, you look high, you look low. Now I see a little dot right there. It's at 2. So, again, on this one, I would give you one check for finding either limit or the general limit, and then I would give you one check for finding the function value. F is not continuous at x equals 6, check, since 5 does not equal 2 or 2 does not equal 5, check. There you go. Since f of 6 equals 2? Well, it's not the fact that f of 6 equals 2. It's the fact that f of 6 equals 2 and the limit equals 5. And 2 doesn't equal 5. So, again, it's super easy. If you get your three things up here figured out, then you could just refer to them down here as their numbers. Either they all three equal each other, any two numbers don't equal each other, or one of them equals DNE. Those are really the justifications. Now, you should be able to work backwards over time. And if I didn't give you the graph, I should be able just to tell you, hey, if I have the limit from the right being 4 and the limit from the left equaling -2, regardless of what the function is, what type of discontinuity do we have there? We know it's not continuous, but there's a jump. So a jump, again, is a consequence of how it's not continuous. We have the limit from the left and right going to two different things. Same thing on the A and C. If the limit exists, the limit is 2, but either the function value doesn't exist or it does exist, but it's a different number. What type of discontinuity do we have? A whole. Good. Okay. So you can work backwards as well. All right. Now, are we always going to have a graph? No, we're not. So you will have a question tomorrow on the quiz, and we have 4 minutes to get this one done. But you'll understand it. Watch this. I want to know if it's continuous at 1. So I will specify the x value. Notice then, to the left of 1 and at 1, it's defined by this parabola, which is continuous everywhere. All polynomials are. So it's going to stop at 1. And then this radical function picks up at 1, and runs to infinity. So I just want to know at x equals 1, are they exchanging the y values correctly? Well, let's see without graphing it. Same thing. At 1, we'll say what's the limit as x goes to 1 from the left of f? What is f of 1? And what's the limit as x goes to 1 from the right? Now look how easy this is. Because it's defined by two different functions on either side of 1, you have to look at the two one-sided limits separately. But from the left of 1, that's your less than piece. F of 1, you're looking for where it's equal to negative 1. And from the right of 1, that's your greater than piece. So you can actually now just use that and use direct substitution. Watch this. What is the limit as x goes to 1 from the left? Well, left of 1, it's defined to be the parabola. So just plug in your 1 into x squared plus 2x minus 3. What do you get? Plug this 1 in right here for x. You get 1 plus 2 is 3. 3 minus 3 is 0. So this parabola is coming in and it's stopping at the point 1, 0. Oops. So the y value is 0. Now notice because it's less than or equal to, when I want f of 1, I need to find where it's equal to. So this says when x is 1, we're also using the parabola. So it's also 0. And you can immediately look at it. When it says less than or equal to, you immediately know that the left-sided limit and the function value are the same. It's the same company that's building the road coming in and the bridge. But now we got to check coming in from the right or leaving from 1. Plug a 1 in now to the bottom piece, and what do you get? 1 minus 1 is 0. The square root of 0 is 0. 0 times 2 is 0. All right, so greater than is to the right of. Is it continuous? Check, check, check. F is continuous at x equals 1. Check. Since, and it's as easy now as saying 0 equals 0 equals 0. Check. And when you say that, I'm not going to be like, which 0 are you talking about, man? Talking about those. Now we have a minute and a half, so I want to just jump over to this other one. And let's talk about it. I don't know if I'm going to have time to write it. Left of negative 2, it's this function. To the right of negative 2 and at negative 2, it's this function. Let's just talk about it. What would be the limit from the left of negative 2? Direct sub tells us it's what? Negative 3. So the limit from the left of negative 2 is negative 3. What's the limit from the right of negative 2 as well as the function value? Plug in a negative 2 here and you get 4 times a half is 2. Does negative 3 equal positive 2? No. So you'd say G is not continuous at x equals negative 2 since negative 3 does not equal 2. Or what would it be? 4, it would be 2 minus, it would be negative 1. Sorry, we didn't subtract 3. The limit from the right and the function value are going to be 4 halves minus 3, which is negative 1. But negative 3 does not equal negative 1. So there would be a jump there, right? All right, so that's it. You'll have one equation like this tomorrow. Practice the notation. Go to the worksheet. And then after the quiz, we'll finish limits tomorrow. Have a great afternoon. And I'll be here in the morning at 7 if you have any questions. Yes, yeah, you use the less than piece. Always. All right, have a great day. Au revoir. Auf Wiedersehen, Kroner. I said goodbye. I'll see you later, Kroner. Yeah, yeah. Feeling better, Tate? Feeling better, Janie? Were you with Colonel for a little bit?